GCSE Physics boosters, magnets. This is the first video in a big long section, a big playlist all about magnets and electromagnetism and magnetic machines, and it's a big one. Anyway, here we go. Magnets. Some pretty basic stuff to start with. So this is a permanent magnet, because it's a magnet all the time. It's a permanent magnet, and if it's in this shape here, we call it a bar magnet. And it has a north and a south pole. A pole just means the end. If it's got one end and another end, then that's a pole. Yeah, it is polar. North and south, because if you dangled it on a piece of string, then the North Pole would point north towards the North Pole of the Earth. So it's the north seeking pole, and the South Pole would point towards the South Pole of the Earth. It's the south seeking pole. The poles are actually where the magnetic field is strongest. Okay, the poles are where the field is strongest. Basic stuff. I'd be surprised if you don't know this. Unlike poles attract. So a south pole and a north pole attract each other. A south and a south repel each other. North and north repel each other. Okay, and it's an example of a non-contact force. Like in electric fields and gravitational fields, the objects don't have to touch each other to exert a force on each other. It's a non-contact force. Now, this nail is made of iron, and iron is a magnetic material. Learn iron, steel, cobalt, nickel. They are magnetic materials, and that basically means you can make them into a magnet. Okay, and they experience a force in a magnetic field. Now, at this point in time, this nail isn't magnetized, but if we put it in a magnetic field, okay, then it becomes a magnet. If we put it in a magnetic field, it behaves like a magnet, and that's called induced magnetism. And because it's behaving like a magnet, it's going to be attracted to this permanent magnet. Note that this induced magnetism is always attractive. Okay, so the left-hand end of this nail will become a north and be attracted to the south. Induced magnetism is always attractive. When we take it out of the field, then what will happen is that its magnetism will usually fade away pretty quickly, unless it's a very strong magnetic field, and then we might actually make it into a magnet, into a permanent magnet. But usually its magnetism will fade away pretty quickly. But this is induced magnetism, it's called. Magnetic fields are invisible. We can't see magnetic fields. If anybody says, what does the field look like? You say, I can't see it, it's invisible. However, you can investigate the field using a plotting compass, which is just a little compass, and you put it in lots and lots of different places, and you see what direction it points in. And that tells you the direction of the field at any point. Then you can draw a diagram showing these things. Now, they are imaginary, they don't exist. But on our diagram, they are magnetic field lines, and they show the shape of the field. They show the direction of the field. I'll talk about that in a sec. And they show where the field is strong and where it's weak. Okay, the direction of the field, we say, is the direction of the force that would act on another north pole. So if I put a north pole where that compass is, it's going to be attracted towards the south. So that is the direction of the field. The direction of the field is the direction of the force that would act on another north pole at that point. Okay, the strength of the field gets weaker as you move away from the magnet, and the field is strongest near the poles. And you can tell that by how close the magnetic field lines are together. So magnetic field lines are an imaginary thing, but they're very, very useful for telling us the shape and the strength of the magnetic field. The Earth produces a magnetic field, and the field is actually produced by all of this metal, this molten metal in the Earth's core. And because the Earth is spinning and because this molten metal is sloshing around, it produces a magnetic field. Okay, and a compass is just like the compass we had with the permanent magnet. Okay, the compass, the north of the compass points towards a south pole, a magnetic south pole. So without wishing to confuse you, that must mean that the Earth's north pole is actually a magnetic south pole, and the Earth's south pole is actually a magnetic north pole. Blimey, that's interesting.